Thank you very much for the invitation. So, my family name, you pronounce it as Van et Wout. So it's Elwin Van et Wout. So I'm Dutch, but I'm now in Chile, like Ganesh told, in an Institute for Mathematical and Computational Engineering. So it's a new institute, founded only in December last year. So at the 30th of December last year, it was officially founded. And then there's an institute that's doing research education in applied mathematics with an engineering outlook. So I wanted to start with a couple of examples of engineering applications for which I use mathematical modeling. So this is a problem I started in UCL in London, and it's about liver cancer. So over here we see a part of the body. So there's a lesion of tissue, and this part is a liver cancer. So there's a small part of cancer. If you have liver cancer, you're diagnosed with liver cancer. The normal procedure is surgical resection. That sounds very interesting, but that's basically open up your body, cut part of the liver out of it, and throw it away. You can live with half of your liver, so it is fine, but there's loads of risks. You lose a lot of blood, you have risks of infection, and yes, you have to live with only half of your liver the rest of your life. So the idea is to use non-invasive techniques, and one of them is ultrasound. So here you see a device and many small ultrasound sources. And the idea is to focus it on the liver cancer and burn the cancer cells. So if you focus all the ultrasound rays into one point, then you burn the tissue, and of course you want to burn the cancer, not your liver. That's the whole point. You can test it. So a pork and phantom is also a nice word for a rib taken from a dead pork. And then you put it in a water bath and you can do tests. We want to do it mathematically with a model. Another example is the following. So I live now in Chile, in the north of Chile. We have the biggest telescopes in the world, in the mountains, high in the mountains. This is one of them. So this is high in the mountains of the Andes. This is the Atacama Cosmology Telescope. You see over here the mirror. This is the primary mirror. So signal from the sky, and we have a very clear sky over there, bounces from the mirror to the secondary mirror and then to the measuring devices. If you look very closely, this is not one panel. These are all small panels pieced together. So if this would be a pure parabola, you will have perfect reflection inside the measuring device. But you have all these small gaps between these panels, these metal panels. So this is a cartoon of a simulation where you have a parabola but cut into half. So the question is, what will happen if I have a full telescope or full mirror and only two pieces, half pieces? And you see the difference is the green one, that is for a full parabola, and the purple one is with this gap between it. Of course, then the next question will be, what will be the influence of all these gaps between these mirrors? And for sure there is a difference. And the question the engineers have is, if they look at the signal, so they receive the signal, and they want to search for black holes, for stars, and the Big Bang in these signals. And this signal, it's easy. I mean, that is the main lobe, but that, you see the moon, but that's not interesting. You want to see something interesting that is indeed in the side lobes, the very small details. So, is this very small detail in a signal, is it actually an interesting star, or is it just influence of the gaps in your mirror? That's the main question you want to answer. The third example is the following. So imagine you're in the army, in the navy, you want to detect submarines. So we use a sonar system to detect submarines, but there are also fish in the sea, in the ocean. Fish just flash, so doesn't reflect loads of acoustic energy. So it just goes through the fish, you won't see the fish on your signal. What will happen every now and then is you can sonify the fish, and you can hit the resonance frequency. So if you hit the resonance frequency, you can see the fish on your signal, but only at this resonance frequency. And this resonance frequency also depends on the number of fish in the school. So why do you hit the resonance frequency? This is an X-ray of a cod. So a cod, you eat with the fish and chips. So you might have eaten this with chips. And then the X-ray you see is bladder. This is the swim bladder. So it is a bladder of air inside the fish, and the fish use it to float. So they can burp out the air to get higher, or they can intake air from the sea to get lower. So they use it to float as a floating device. Not all fish have these swim bladders, but many of them do have. Trout is one of them. And air has very different material properties than water, so that's why you can hit this resonance frequency of the fish. And then all of a sudden, this school of fish looks like a submarine. Yeah, that's of course something you do not want in your signal. The other way around, if you are a biologist, you might want to see the fish. Actually, you might want to count them. So that's another application in the same area. So all of them, yeah, you can do physical experiments, but there are problems or limitations with physical experiments. One is ethics, for instance, in medical imaging or medical. Yeah, who is willing to go to the hospital and we're going to burn part of your body and we'll see what will happen. That's no one would like to do this. High cost, so the telescopes, these are billions of dollars worth, so it's very expensive. And also, yeah, accuracy. The physical experiments have limited accuracy. So, yeah, for instance, this fish would look trying to get a fish swimming in the way you want to let him swim and do some experiments on the fish. So there are problems or limitations with physical experiments. So we want to use mathematical modeling and computation to get some new insights in these applications. So in the first part, then, yeah, how do we model? Yeah, we will just look what are actually the main phenomena we have in these three different applications. So all these three applications, we have a wave, might be an acoustic wave, might be an electromagnetic wave, we have objects, we have a telescope, we have a rib, we have a fish. So we need to calculate the scattered field out of this instant wave field that's scattered by these objects. So these are all the same for these three different applications. And these have more in common. So each of these objects, so we have not only one fish, but a school of fish. We do not have one rib, but we have multiple ribs. We do not have one panel on our telescope, but we have multiple panels. So we have multiple scattering devices. The other thing is the instant wave field typically has one dominant frequency. So the solar system is operating on one dominant frequency from the signal from the sky. Yes, there are many different frequencies, but you're interested only one or a small range of frequencies. And also in the ultrasound, you also have one dominant frequency. And moreover, there are no really interesting effects in time. So there are no nonlinear effects. It's just a metal plate scattering waves. And interesting is also we have unbounded exterior regions. And this is a bit more of a model design. So we just assume that the sea is infinitely large. We assume that the sky is infinitely large, and also that in the case of the rib cages, we can model the entire body as water. So it's basically unbounded. And this is important because if we get the mathematical formulation, so we're looking at frequency harmonic waves, so frequency dependent waves. So we have the Helmholtz equation. This is the Helmholtz equation. We have boundary conditions at the boundary, so at the boundary of the telescope, of the fish, or the ribs. And we have a boundary condition at infinity. So an unbound region, so at infinity, we have a boundary condition. This boundary condition is called the Sommerfeld condition, and it states that all scattered fields are going outside. So we only have radiating fields at infinity. We don't have waves entering at infinity. These boundary conditions, they depend on the application. So we use rigid bones. We have a conducting mirror for the telescope, and we have penetrable bubbles, so you also have a field inside. So these boundary conditions do change for different models, but for this presentation, everything goes for whatever boundary conditions we have. So when we have this Helmholtz equation, in general there are no analytical solutions, so we need a numerical discretization technique. So you could do finite element methods. The problem with finite element methods is this unbound region. So if you have an unbounded region and you want to use finite element methods, you have to bound it somewhere in your region. So you need an artificial boundary condition. Yes, it's possible, but it's not really what you want. So instead you can use what we call the boundary element method. The main idea about boundary element method is the following. So if we have a homogeneous domain, like air, we have a source and observer of a wave. What will happen if we have a source, we have an observer, then we have a wave? The wave is not going to change in frequency in air. The direction is neither going to change. The only thing that's changing is the amplitude. So you have less energy far away. But we also know that it's 1 over the distance. So the whole point being is, in homogeneous medium, we know how a wave propagates. So if we already know it, we do not want to calculate it. We do not want to approximate it. So what do we not know? So at the boundary, how does it reflect from a boundary? How does a wave reflect from a mirror, from a fish? So at the boundary, we have scattering and also penetration, and that's something we do not know well analytically. So that's the idea. We plug in the Green's function. So the Green's function is basically saying in homogeneous medium, we have a constant, or the wave number does not change, the direction does not change. The only thing that changes is that the amplitude is 1 over the distance between a source and observer. So we put this in our model. Instead of using a discretization technique for the fields, we reduce everything with the Green's formulas to the boundary or the interface of our object. So we reformulate the Helmholtz equation in the field, in the volume, to a boundary equation at the surface of the object. That's the whole point of boundary element method, because the scattering at interfaces, that's the interesting part. The exterior field is not that interesting, but if you have the potential at the interface, you can also compute the fields in exterior or in interior. So once you have the potential at the surface, you also have the solution in the exterior. And the whole point is we only need a formulation at the surface, so this external medium that is unbounded is naturally included in this model. So we don't have to care about absorbing or artificial conditions at infinity. So at the surface we have our integral equations. So we need to discretize at the surface. So here I have 2 examples of a sphere. So you see we use triangular elements on the surface. So we discretize, we mesh the surfaces with triangles. At the triangles, very similar to finite element methods, we need to choose test and basis functions for our variational formulation. These are piecewise constant functions, and these are piecewise linear functions. In the case of Maxwell equations, you need vector functions. So you need what we call the RWG functions. So these are vector functions, but this is scalar. So we have constants on each element, or piecewise linear on each element. So these are the test and basis functions we use. And again, it's only on the surface of the object, nothing in the volume. So far it looks like a finite element on the surface. However, it is quite different if you really look at the properties. Because what will happen in our, from the Helmholtz equation, we go to this boundary integral equation on the surface. So we go to the volume to the surface. This also means that at the surface, we have point-to-point interactions. So every triangle is a source and observer, and we have point-to-point interactions. So imagine that if everyone over here is talking and also listening, and everyone is a source and observer, and you have to collect all of them and do all the point-to-point interactions in your model. That means that you have a dense matrix. So you have a dense matrix. So after discretizing, you get a dense matrix. Well, that's not a problem because it's just a matrix, but you need to be careful with the storage as well. And that's also why you cannot just use finite element techniques straightforward for boundary method, because they work for sparse matrices and not for dense matrices over here. The other problem is, if you see the Green's function, what will happen is x is equal to y. Well, the Green's function is not defined. So if x is very close by y, then you have a singularity. So we have singularities in the formulation, but we don't only have the singularity of the Green's function, we also have integrals. So we can integrate out the singularities. So it's all possible, but you have to be careful with your quality rules. Those quality rules are typically defined for smooth integrants. Now we have a singularity, so we can integrate it out, but we need special quality rules to do this carefully. Otherwise, your solution will not be accurate. So these are two main challenges in boundary element methods. But boundary element methods have been used already for many years, so there are very good schemes for these quality rules. It also means that implementing a boundary element method is not as easy as implementing a finite element method, or for sure not as a finite difference method. So it's a bit of a headache to implement them, especially in 3 dimensions. Luckily, we have a open source software. So boundary element methods, these are available in commercial packages, large one like COMSOL and ANSYS. So I've been working together, actually started in London with Professor Timo Betke already, I think, 8 years ago. Ganesh has also been involved in the early days, I think, and I've been working on it since a couple of years ago. So it's a open source package. You can just download it from the website. There's a Python interface, so it's easy to use. Python is also open source, and you only need high-level instructions, so you don't need to go into the C++ core. Because behind the Python interface, there is a C++ core that's doing all the computations efficiently. It works for acoustics and electromagnetics. So the idea is you just specify your formulation, your basic test functions, and you can run it in the Python, and you can visualize it in Python as well. So at this point, yeah, the question is, yeah, why do we care? We have a boundary method, already old. We have software, so we just hit the software to a problem and we're done. Yes and no. For sure, you can just run it, but there are problems. So there are challenges because of, for instance, resonances. So think of this fish. We need to find the resonance. Typically, software works very fine outside the resonance. But if you hit the resonance, then you get problems with singularities of your matrices. And yeah, not all commercial software or open source software will be stable anymore. And that's exactly what we are interested in with resonance. So we are interested in the phenomena for which the software is not designed. So that's why we have to look into the machinery of boundary methods and do something better. Yes, yes, yes. Yes, it's in the physical problem, and that's also why your displacing matrix will become very poorly conditioned. Yes. So the linear solvers might not converge anymore. Yes. Also, if I want to specify a very high accuracy, not always possible in standard software. And for instance, in medical applications, I do want to have a very high accuracy because we are talking about people we wish to heal, and so we might want to have more capabilities to set all the flags and put all the parameters to get high accuracy and to really know what's happening. Another thing is, software is designed for a very broad area of application. If there's only one application, I can include some information and actually outperform commercial software. So these are the reasons. And give you an example. So here we have a nice guy with some ribs, and the red part, that is the liver. So your liver is over here. So the idea is that if there is some kind of small cancer cell just at your liver, you would like to treat it with these ultrasound devices. So they use ultrasound devices to treat cancer already in many hospitals, mainly for types like breast cancer. Because in breast cancer it's very soft tissue, so there's no scattering whatsoever. In the case of a liver, you can already see the problem. We have these ribs in between. So we need to get this ultrasound through the ribs, or through the rib cages. Preferably not through the ribs, but through these openings between the ribs. So you have scattering and also absorbance of these ribs. So it's not that straightforward, and that's why they are not still not using for the liver on a high scale. Only in very isolated cases they use ultrasound for livers. So we would like to do our boundary method for this ultrasound application. What is the challenge? The following. So we are talking about wave vibrations or wave phenomena. So if we want to discretize a wave, here we have a wave, we are discretizing with piecewise constant elements. So I need for sure 2 elements, but in practice I need around 10 elements per wavelength to do the computation accurately. How large is a rib cage? Well, 20 centimeters. What will be the frequency we use? 1 megahertz. So the reason to use 1 megahertz is that the wavelength at 1 megahertz is 1.5 millimeters. That's because we assume that the bacteria is water. So we assume that your body is entirely made of water, which makes sense, at least near liver. So liver is almost the same as water, tissue is almost the same as water. A rib cage for sure not, bone no. And also if you look into the treatment technology, they put a patient on a table with a water bath. So the instruments are in a water bath, so everything between the source to the ribs is almost like water. So in water 1 megahertz will be 1.5 millimeter wavelength. Why do we need a high frequency? So if we have a high frequency, we have a small wavelength, and we want to focus on the liver, on the cancer cells. And the region of cancer is in the order of millimeters. So we want to burn, a region of millimeters, centimeters. So if we have a wavelength that's way bigger, we can never focus it in this small region. So we need in a very high frequency to focus it in a small region. Why don't we use 10 megahertz? So if you increase the frequency, you get more absorbance in water. If you have more absorbance between the source and your liver, then all the energy is absorbed in between, and you cannot burn liver anymore, or not the cancer cells in your liver, by the way. So you need 1 megahertz to reduce between 1 and 1.5 megahertz, not higher, not lower. That means 10 elements per wavelength, 10 centimeters, 1 megahertz, we need 500,000 unknowns. 500,000 unknowns, so if you're familiar with finite element methods, that's not that big. For boundary element methods, it is. What's the problem? So not only the computation time, we need to store the matrix. So storing a matrix in your program is easy, with a 2 by 2, everyone can do this. Storing a 500,000 and 500,000, we have the following problem. We need to store 2 dense matrices. We need double precision. These are also complex numbers, so 128 bits. Now, who is quick with calculation? 2 times 500,000 squared, that's 128. How many bits? A lot, yes, a lot. 7 terabytes. 7 terabytes. So we need 7 terabytes to store it. And we don't only store it in our hard disk, we need it in the RAM. So we need to calculate, we need to do multi-factor multiplication. So my computer and laptop has 16 gigabytes of RAM, so no way I can store this. I just looked up in the Amazon cloud. So the biggest node they have is actually 4 terabytes, which is really, really a lot. But you have to pay $27 an hour. So 4 terabyte RAM, you need to pay $27 an hour to Amazon Cloud, and still you don't have the 7 terabytes. So what do? We have to do something smarter. We need to compress the matrix. It's the same as going from BMP to JPEG, photo, you can compress matrices. So the idea of this matrix compression scheme is the following. So the results are very good. So we can compress with 2.7%, so 200 gigabytes, and that's reasonable for a proper cluster, decent high-end node. So what's the idea of this compression? So remember, everything comes from the Green's function. The Green's function is the main building block in boundary methods. So the Green's function is singular when you have source and observer very close by. But if they're very far away, it's very smooth. So you could approximate that. Or otherwise stated, imagine if, again, in this room, everyone is a source and observer. We can group. We can do the left half and the right half. We just group the right half, the left half, and then we do mean, or like some average over here and transfer to the average over there. And then within it we can do by row or by point. So that's also the idea of fast multiple methods, also of compression schemes. So over here, these are all far interactions. So there are a bunch of nodes over there, a bunch of nodes over there. So we just take an average of this, average of that, and we transfer it. Or mathematically speaking, we take a block of the matrix and we use a low rank approximation. So this is 500,000 times 500,000. This will be around 100,000, this block, but we use a low rank approximation of 140. So we have 140 times 100,000 vectors. So you can compress this matrix to 2%. That's the idea of this matrix compression. So now we can store the matrix. So we can store the matrix in our RAM. We can also do a matrix times vector multiplication with this compressed scheme. So now we can solve it. So yeah, the whole point, this is again similar to as finite element methods. We need to solve A axis B. A, the matrix of 500,000 is 500,000. We use, of course, you can do a direct solve and LU factorization, but that's very expensive. So we use iterative linear method, GMRES. So we iterate to the solution. So I'm not sure if everyone knows this method. So if I have a the matrix, a vector in 3D, then we have somewhere a solution. So we start somewhere, we search in one direction, second direction, the third direction, and we find a solution. Now we need to find a solution in 500,000 dimensions. So you're still iterating, and after around 100 iterations, you are close, sufficiently close by your solution. So that's the idea. But we want to do this faster. So instead of 100 iterations, so every iteration you need to do a matrix times a vector multiplication. So we want to reduce the number of iterations. The standard technique is preconditioning. So the idea of preconditioning is the following. So if we start somewhere and we know more or less where the solution would be, we're not going to search that direction, we're searching that direction. And in one iteration, we're already close by. So you search in the directions you expect the solution to be. So you expect to have less iterations, but the whole point is, how do you know where the solution more or less is? You don't know the solution. The idea is that you might be able to cook up an easier model, that's easier to solve, but not as accurate. That's the whole preconditioner, so the M. So on a linear algebra level, you look for an easy to solve matrix that looks like A. So M is the matrix we need to find. M needs to look like A. That means that we are going very fast in our iterations. But yes, every iteration we need to solve M. And easiest matrix to solve is the identity. So it looks like the identity, it's easy to solve. So we need to find a matrix that looks like the identity and a complicated matrix A. So somewhere in between, we need to find an M. And if you're not very clever in choosing the M, you can actually increase the compute time. So it's not that evident at all. So what's the M I use? Well, this. Does it look like identity? Well, not really. Does it look like A? Not really. Why does it work? It actually works. So this is my preconditioner. So for the people who know boundary methods, we have the identity operator, the double layer, and over here the hypersingular, so it's a Burton-Miller formulation. And we only precondition the hypersingular, because that's the most complicated matrix. Anyway, so why does this preconditioner work? So this preconditioner is designed for a high frequency model. So if we take the model and take the frequency to infinity, we can do some approximations. So for frequency infinity, we have some approximations and we use this as a preconditioner. No, we're not at frequency infinity, but we are very large frequencies. So it looks, very large frequency is almost infinity. That's why it looks like the matrix A. And that's also why this works, for instance, for the ultrasound, but not for the bubbles, because that's low frequency. So this preconditioner, we choose it because we know we have high frequency, so we use a model that's based on frequency infinity. It's also easy to solve, as neither that obvious, but we use a Padé approximation of this minus and half. What you see is over here the Laplace-Beltrami operator. So that's the Laplace operator on the surface. Laplace operator is a local operator, so if you discretize it, it's a sparse matrix. So we get a sparse matrix, or actually, if we get 5 sparse matrices, we have some kind of series approximation. So we precondition a dense matrix with a couple of sparse matrices. Solving a sparse matrix is way easier than solving a dense matrix. This is sparse LU, and you're already finished. So that's why it's easy to solve. Does it work? Yes. So yeah, here I compare 2 different formulations. So the blue one is a standard one, the Burton-Miller. If we precondition the blue one, we have the green line. For the green line, here we have wave numbers, so frequency, low frequency to high frequency, and this is a number of GMRS iterations. So this is another formulation, the Bragg-Hager-Werner, and you can also precondition with different preconditioner. The point is that, yeah, if you do the standard formulation, you need 60 iterations. Now we need only 10 iterations. So we reduce the number of iterations by 6. That doesn't mean that we are 6 times faster. No, but like I explained, we have less iterations, but every iteration is more expensive. So it doesn't mean at all that this will be fast. However, the preconditioning step is only 1% overhead. So this iteration is 1% more expensive than that one. So we gain a factor of 6, we lose 1%. So yes, it's way fast. And if we run this, it took me a couple of hours on a desktop machine. Then we have the result. So here we have 4 different rips. So the solution of the boundary methods on the surface. So this is the surface potential, basically the pressure on the rip. That's the solution of our model. It's also a quantity of interest, because you might burn the rips. Here you see a very high pressure. So the question is if this pressure is too high that you burn the rib. So this translation we still have to do. What you see in the field, you see all these small waves. So you see the high frequencies, you see your shadow regions, you see over here the focal spot. So what you can see is that the focal spot doesn't change that much with the rib. So it's actually good. So we can focus behind rib, because the source is over here. So you move it over there, transmit all the energy over there. So this is the computational simulation for engineers. They want to have the pressure field, because if the tissue is heated over 40 degrees, it will burn. You get the blaze. So, I mean, where is the 40 degrees contour? Yeah, that's something we still don't know, and that's something we're working on. So, the second question. So we have a software, we have a model. Are we done? Just, we are finished. Yeah, not always. Not always a good idea just to use one technology. And I think this is something that is always at the forefront of in science and engineering. But yeah, there's no such thing as the best technology. I mean, I enjoy boundary methods, but there are many reasons why boundary methods are better than finite element methods. But at the same time, there are many applications where you simply need finite element methods, and boundary methods do not work. Depends on what kind of phenomena do we want to include in a model, how accurate do we need it to be, and also what are our limitations on the resources. So there's no such thing as the best methodology, and also if you design new numerical methods, is this actually correct? Can we compare it with standard technology or other technology? So I would wish to talk a bit about that, and on the lines of this application in the astronomy. So here we're in Atacama again. Here you can clearly see these different panels for the mirror. You see over here the star. So this is a really big telescope. It's around 20 meters diameter, I think. And these are the big mountains. These are around 5,000 to 6,000 meters high. So feet times 3. You do the calculus. or switch to standard units. The primary mirror is 6 meters, you have 71 panels, and observations are between 145 to 80 gigahertz. So that means that we have a system of around 5,000 wavelengths. So before I was talking about high frequency in the rib cages. Rib cage is around 125 wavelengths across. And we really needed everything to get this working, all the tricks we knew. So 5,000 wavelengths across is never going to work. Neither with this Amazon cloud with 4 terabytes of nodes, if you have loads of money. So what you need, physical optics, physical field diffraction, these are approximate methods for very high frequencies. So these work very fine. The problem of these is that they use approximations to very high frequency. The gaps between the mirror are in the order of a millimeter. So you can place them together, but you have a gap of around a millimeter. The wavelength is also around a millimeter. So inside these gaps, you expect reflections, diffractions, all kinds of interesting phenomena that physical optics is never going to capture. So this is a problem because they're running the physical optics and they don't know if this gap has influence on their results or they have ideas. But you want to test it. So you have inaccuracies in the side lobes. So what we did, we compared physical optics software called GRASP. This is one of the most standard softwares for astronomy. And we compared it with BEM-PP, our open source software. So you have these two half mirrors, the picture I showed in the very first slide. So you have a parabol cut into half. So you see you have a very nice circular shape, but over here you see the influence of the gap between these two halves. What's the difference between GRASP and BEM is this one. So there isn't difference. So now the main question is, which one is better, GRASP or BEM? Now one reason, for GRASP you need to pay $10,000 a year. BEM-PP is open source and free to use. The mathematical or more scientific reason, so remember that BEM is a full wave solver. GRASP is based on physical optics, so you do have more assumptions in your model. So GRASP has more assumptions in its model than BEM, so I do expect that BEM is better performing in this test case than for GRASP. The reason that we can only use two half spheres is because BEM is very slow, GRASP is very fast. So BEM is slow but very accurate, what we expect from the modeling part. So in this case I expect BEM to be better than GRASP, and this would be more or less a difference. And then the question of course is, if we want to do the same but for a real mirror, somehow we will need to couple these two together or do something clever. That's something still open. This, I'm not sure if you recognize, this is a goldfish. So this is a goldfish. Goldfish also have a swim bladder. Actually, it has two swim bladders. You see the swim bladder of the goldfish with almost a sphere. So it makes sense to model this as a sphere. So in this application, again, we want to calculate the resonance frequency of fish. So, and not only one fish, of a school of fish. So we model every bladder as a perfect sphere. So if we have an instant wave field, a perfect sphere, actually we do have an analytical solution. These are the spherical harmonics. So if we have an analytical solution, we can use this solution for one fish. If we have two of them, we cannot use the spherical harmonics anymore. They do not work for two of them. But you can do that for them separately and couple them together with some kind of clever mass spring system. These are also called transmission matrix methods. So this, in the literature, is considered as the best or the most standard methodology for this area. Remember that the mass density of water is 800 times smaller than air. Higher. So these methodologies with these spherical harmonics, they work. But if you get these two very close by each other, then they don't work anymore. So if two fish are very close by each other, these spherical harmonics have very high inaccuracies. And do not only think about fish, but also just water bubbles in the sea. So if you have two water bubbles very close by each other, you cannot use these spherical harmonics accurately anymore. Or you can, but you need 56 digits accuracy. Yeah. I mean, everything is possible, but not really what you want. 56 digits accuracy. So here was the whole point. This is the solution of one bubble. This is the backscattered field. So we hit the bubble with a field and we measure the backscattered field. This would be for the rigid sphere, so this is the famous mesospheres. If you have a penetrable object, then you have loads of high frequency resonances. These are the standard resonances of a bubble or other objects. You have a really large peak at low frequencies. So I say over here wave number, that's the wave number for a sphere with radius 1. So it's a non-dimensional wave number basically. This is very low frequency. And we are interested in this peak. So that's the peak where sonars operate and can hit these fish. This is the peak you will see as a low frequency resonance of fish. So we compare the team matrix with our BEMPP, use a multi-trace formulation, and please remember we are really very low frequencies. So the wavelength is 500 times larger than the bubble radius. So if the wavelength is from that wall to that wall, the bubble is around a centimeter or so. So it's a very low frequency. So before I thought we need 10 points per wavelength. So if I have my wavelength from the wall to the wall, use 10 points, I have a mesh like this, but I have a bubble like this. So that doesn't make any sense. So with meshing, it's not about only 10 points per wavelength. I also need to capture my sphere. And if I mesh my sphere with very coarse mesh, the resonance will change because the resonance depends on your shape of the object. So it sounds very easy, low frequency sphere, but actually I need a very fine mesh. Surprisingly, because I'm interested in resonances, and also because these are very close by each other. So here I hit these two bubbles with a wave field. These two bubbles are not touching, so there is a distance of 1% of the radius between them. Also, these bubbles are penetrable. So I have a field inside the bubbles, but because we have this contrast of around 800, the field is around 800 times smaller. So in this scaling you won't see it. In the logarithmic scaling you will see it. Interesting thing is what's happening with this low resonance frequency. Low frequency resonance. So if I have one sphere, I can calculate the backscattered field, and where you have a peak, you have a resonance. So we have 0.0136 for one bubble. If I have two bubbles, the resonance frequency will change. So for two bubbles, we have the green line, so we have a downward shift of the resonance. For three bubbles, as well. So now the question is, if I have 4, 5, 6, or about 100 bubbles like in a fish pool? Yes. So with my BEMPP, it's not efficient, so I can't do this on my computer. And actually that's also the reason why I'm over here, because AMS has a very fast method for many bubbles. So that's one of the reasons I'm over here. Another thing that's interesting is, if I have one sphere, and they have a bubble far away or close by, you also have different resonance frequencies. So the closer by, the larger the downward shift. So this is, with a distance of 1 radius, is 1% of the radius. So you'll see also influence of the distance between the different bubbles. So I'm using my BEMPP. My colleague in Chile is using his T matrix with 56 digits accuracy. So we have a difference of 0.18%. So two relative quite different methodologies, only 0.2% difference. it's very comforting. So I'm very confident we are very close by the actual results. We also tested for one bubble with the analytical solution, and then we're even closer by. So finally, I would wish to discuss. So we now have two different methodologies. Could we validate this with physical experiments? So there has been attempts to do physical experiments for these fish. Back in the days, they did let a goldfish swim in a tank and solidified it. I don't know if the fish survived it, because it was just before dinner and, and they had something for dinner. Anyway, so you can think of a tank with bubbles, but then you have still the same problem. How do you keep two water bubbles very close by in the water? So it's physically very complicated. So imagine that not having two bubbles, but one bubble very close by the wall. So if you think one bubble and the wall, with a map of images, it's the same as two bubbles with the correct boundary conditions at this half space. So one bubble very close by a wall is the same as having two bubbles in this model. With the correct boundary conditions, you have different one at the wall and one at the subordinate interface. And that also brings us to a different experiment, because if I have two bubbles, very low frequency, it will be excited with almost the same energy, because the wave is almost constant. What I can do in this case, I can excite one bubble, the opposite phase than the other one. So I change the instant wave field, so that the left one is excited minus the right one. That's the idea. That makes the field zero in between them. So this wouldn't be physical, but only physical next to a wall. This is a different system. So you can imagine if they have two bubbles, normal system is a low frequency, so they are excited at the same energy, so they are in phase. They are just moving like this. If I do the other phase, they are excited like this. So they are vibrating in opposite phase. So we have the same geometry, different instant wave field, and they get a different resonance, or actually a different peak. We have as a peak. If you have bubbles in the same phase, you have a downward shift of resonance. If they are moving like this, you have an upward shift in resonance. So that's interesting, because you do not change the geometry, only the instant wave field. How can we think about this? So this is a picture I made in Santiago. So I always take the tube to the campus. This I made in winter. So you see people are walking with coats. Also in Chile it can be very cold, around 40 degrees Fahrenheit. That's very cold for Chile. Right now it's 95 degrees Fahrenheit. In Chile it was the summertime. Anyway, what's more interesting, it's sometimes very full in the metro, so you're very close by other people. So what might happen is that I'm in the subway and there is a guy with a beer belly next to me, and we are breathing. So what will happen if we all breathe in the same phase? I will feel some kind of resonance. I might not touch him, but you might feel resonance, and you're going to breathe slower and slower. If we breathe out of phase, we're going to help each other. So it's a higher frequency. And that's the idea. So if you think about these bubbles in water, they can help each other, or have a problem with each other. So that's the idea why you have this upward shift out of phase and downward shift in phase. So that's the interesting explication of this phenomenon. Just to finish, so many interesting examples, and I would wish to say, these boundary methods, they are not very common, but they do have very important applications where they are simply better than finite element methods. And we still want to do many more things. For instance, in this ultrasound, inside the focal region, you have nonlinear effects. So you would like to couple the boundary method with a nonlinear model inside this focal region. For this telescope, we need very high frequencies for this large-scale problem. And for this fish, like I said, that's one of the reasons like Ganesh and me trying to collaborate. We need 3 fish, but we want to do it for thousands of fish. How do we do this? Yeah, we need to do probably different methodologies, a couple different methodologies to get many different fish. So that's it for today. Thank you.
Ask Elwin to give a non-technical talk about equation. I think he's done a wonderful job. I can certainly watch for that train business. That's why I stopped going to Chile after 2014 and missed it. But you took a right train. Okay, so the technical part of this talk, in particular the fish problem and so on, I think he's going to give a seminar on Wednesday. So that's what the seminar is reserved for, wherein you can give them a lot of technical data and support. In particular, as you mentioned before, I asked that question, 500,000, you know, it's 50 degrees of freedom, yeah, 20 terabytes. Actually, the reason why this year, in some senses, recently I've done something with more than 10 million nodes. So it can be done in a very high performance computer at a different way. So there is a possibility the technology can be used in a different way altogether. But this is quite exciting way to think about it because a lot of applications. So this is in particular for students if you guys are interested in this sort of a thing. But this is one of the exciting areas. If you have time to talk to Elwin about it. So I'll open the questions. Go for it.
So the way you came up with your preconditioner seems sort of magical, but maybe that's because we didn't talk about it for very long. So can you just give us a few comments on how specific that was for this particular PC, and how is there a method if somebody uses them for a different PC to use a similar technique?
Yes. So this preconditioner is based on what we call on-surface radiation conditions. So this preconditioner, so if you think, for instance, in physical optics, it works because you assume basically frequency to infinity, and then you can do approximation. So you can do the same type of approximations if you assume frequency to infinity. So think about kind of elaborate version of Taylor polynomials around frequency to infinity, and then the first term would be the 1 divided by ik, and it's the standard value of this preconditioner. 1 divided by ik is a number, so it's easy to invert, so you don't need to invert anything. So if you take the second term in this series expansion of frequency to infinity, you get a Laplace-Beltrami. So this is the Laplace-Beltrami operator on the surface divided by the wave number. So it almost looks like, if you move the k plus k over there, like the surface Helmholtz equation. So that's why you see somehow a wave on the surface. There's a wave, local wave on the surface. So this works because we assume very high frequency and because we have an acoustic wave. And then solving this is by a Faddeev approximation of the half, the square root, and doing test and base extensions that will result in sparse measures to solve. So this one works for high frequency and acoustics. So if we have different partial differential equations like in Maxwell, so for Maxwell is also wave equation, and this precondition has been attempts to get it working for Maxwell as well, and there are theoretical proofs that it should work, but the numerics is a bit complicated, how to discretize this with your basis functions. There has also been attempts to, or actually publications about this for elastodynamics, so elastic waves. But these are the 3 partial differential equations where you can use this type of frequency, high frequency precondition. So for any other partial differential equations, this is not available yet. And like I said, it's really high frequency. So you also see, I mean, for low frequency it still works, but over here you gain a factor of 4. High frequency you gain a factor of 6. Most preconditioners, like Calderon preconditioners, work better in this region. So I can use other preconditioners, and then I can reduce this by a higher factor of that, but they will increase. And this is the whole point of this preconditioner. It remains constant with high frequency.
Yeah.
Yes. Yes.
That is
Yes.
important. Absolutely. Notice the opposite. In particular, this particular condition changes the fish or the bone. It doesn't allow the bone to be penetrated inside. Moment that you allow bone actually, you allow the fish to get inside. This condition even that problem.
I was going to ask you, I don't know if you, I don't do this,
Yeah.
work with it, but if you have any sort of like other boundaries, not
Yes, yes, oh yes, yes,
every single
yes,
time.
yes. There's no point of
It is problem.
preconditioner. Yeah,
Okay.
getting a very general preconditioner is awfully complicated, and this works because we know everything about our model and because of the physics we know, and that's also it only works with this operator, the D, not with the K tree. That's why it's preconditioning this matrix with the precondition and not that one. So we really put loads of information in this precondition.
So it seems like the structure and the idea of it is what you like. I was thinking of it as well.
In fact, if you Google voice asking, that's like it. It's a sort of a general idea on this business.
I don't necessarily always have like really large mysteries, but we have like these kinds of problems. We have to solve it a lot.
Yeah.
Right.
Yes. 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 Oh, definitely. If you can get this before that, but then every time in your equation.
Preconditioning. Right. You expect as you get towards higher weight,
Yeah.
the number of iterations will go down to maybe one. Use your preconditioning.
Yes. But that's a good. So if you would do the experiment, if you take your BEM with frequency to infinity, you will basically have the OSSC, but you still have only two terms if you're in your series expansion. So you wouldn't expect one, but you would indeed expect if you have very, very high frequency, you would expect it to be even better than that. Yes. The only thing is computation is not possible anymore. The limit is on the computation. But it's interesting that if you at higher frequency, you expect to have it by the benefit from this condition. Yeah, yeah. The last one is one less than. So there's some wishful thinking it going linearly. Yeah, no, probably not.
In particular for students, a lot of preconditioning. To construct preconditioning itself is more expensive than something going to apply.
Yes.
This is a bigger sheet sometimes going on with that. That's the essential solution. So you can run the precondition everything works with, but if you do the computation, the preconditioner, sometimes preconditioner solving is actually almost same as solving original problem.
Yes.
You got to be a bit more careful. Go for it.
So do you see clustering of eigenvalues of say around one? This is typically what we work with.
Yeah.
Clusters. Have you run any tests?
Yes, yes. So I did run tests on smaller test cases for the spectrum boost, calculating all the spectra. The entire spectrum is very expanded, so I couldn't go to very high frequency. What you do see is that if you just use the standard formulations, you have many eigenvalues very close to zero in the complex plane with a complex matrix. And if you use a preconditioning, these around zero will be moved away from the origin. So you move away the very small eigenvalues away from the origin. That's why you expect, you see more clustering of the eigenvalues away from the origin in your complex plane. And then that's also why you expect, why you could explain the better convergence. It's not like a clustering around 1 point, like 0.1 your axis. That's not the case. Not that easy actually.
Because the physical, if you go back to it, it's like, the reason it's getting close to one is this. So this is a scattered wave. This guy absorbs the wave. That's it. So this epsilon is extremely important. This guy, the complex quantity, is very important. Basically, you just can simulate it scattering. So basically, I want to negate that. So I just put an absorber. So this is basically this term absorbs the waves. Yes. So that is the reason why it works. So that's why the physics part has also played a role. The epsilon is a very big thing that we basically study mathematically now, trying to prove if that's what I know. And that's the reason. So similarly, you might learn the example of whatever you do, something of that sort.
That's indeed. I mean, that was indeed because it's epsilon. It's not something physical, because if you really take the physical model, epsilon will be 0, but then we get informative singularities. So we include a bit of damping, and so this epsilon shouldn't be too big, not too small. And there are guidelines on how to choose this epsilon based on a sphere. So if we have a perfect sphere, we know how to choose the epsilon, but yeah, a rib cage is not a perfect sphere, but it's, in the end, it's a preconditioner. So yeah, you have flexibility to play around with all these parameters. Also with the number of years linear today. So yeah, many small parameters to fit all it.
We normally finish by 4. So I think it's unfair to ask. So if you have more questions, I think Elwin is going to be here for another week. So in particular, if you're interested in going to Atacama or something like that, you can even ask him. So thank you. Thanks for everything.
Thank you very much.